This is a question on acids and bases. It runs from A through to part E and it's worth 15 marks. So try them, pausing as you go, and then review once you've come up with your own answers. Here's parts A and B, C and D, and finally part E. So going back to A, we have here the meaning of the term Bronsted-Lowry acid, so a straightforward definition, and you can do this with two words. It's a proton donor. Now it's important that you recognise when we talk about a proton, we are talking about an H plus ion. So HCl will donate H plus, H2SO4 will donate 2H plus. They're proton donors. And what do we mean when we talk about an acid being strong? Well, again, there is a very specific definition. In this case, it's that it fully ionizes in water. Moving on to part C, and we have a calculation here. We have got a temperature, a volume, and we have got a number of moles of hydrogen ions. So we need to know the pH. Well, the first thing I need to do is work out my concentration of the acid. So I know how many moles of H plus there were, I know what volume there was. You'll recognise here that I have divided my 25 by 1000 because my volume needs to be converted to decimeters cubed. Once I do that, I get my concentration of 0.058 in this case, and I can then substitute that into my pH expression, giving me a pH of 1.24. As requested, I've done that to 2 decimal places. On to part D, and there's quite a lot to this. It's a 5 marker. pH of the solution after the addition of 35 cm cubed of 0.15 mole d to the minus 3 NaOH. So we're still going to have to use information from part C. Now the first thing to do is work out how many moles of NaOH I've added. And if you're ever given a concentration and volume of something, work out the concentration, because you can guarantee there will be a mark for it somewhere, and it might just help you to see where the next step will be for you to take it forward. So that's how many moles of NaOH I've got, 5.25 by 10 to the minus 3. Now if I'm reacting OH minus against H plus, I know that I started with 1.45 by 10 to the minus 3 moles of hydrogen, so I've got an excess of OH minus ions, and I can work out the excess. It comes to 3.8 by 10 to the minus 3. I also now have a new volume because I've put 2 solutions together. So I can work out my concentration of OH minus ions. So in this case, it's that number of moles, 3.8 by 10 to the minus 3, that are left in excess after the reaction, divided by 60. But once again, I'm converting that 60 to decimeters cubed. And that takes you to a concentration of 0.0633. Now I can't use OH minus concentration to work out the pH. I need to convert it, or I need to find the H plus concentration. To do that, I use Kw. And we've been told that Kw has a part to play in this reaction, and we're actually told its value at 298K. There is an expectation that you will remember that. But I can take my Kw expression, I can rearrange it to make H plus the subject, and then I substitute in my Kw value and my OH minus concentration, giving me an H plus concentration of 1.58 by 10 to the minus 13. I can then substitute that in to my pH expression, giving me a pH of 12.80. And I ask myself, is that a reasonable value? Well, we've got an excess of strong base, so I'd expect my pH to be above 7. That seems reasonable. Moving on to part E, another big calculation here. We've got a buffer solution that we're making. We want to know the pH of that buffer solution. 1.5 grams of sodium hydroxide added to 1 decimeter cubed of 0.15 molar weak acid HA. So let's start off with a straightforward mole calculation. We've got a mass of sodium hydroxide, we can find its MR, we know we've added 0.0375 moles. Now if I take a look at the equation here, it's a monoprotic acid and NaOH, so my mole ratios are 1 to 1 to 1 to 1. Now that means that the moles of NaA that I will make here will be 0.0375, because that's how many moles of the sodium hydroxide I've added. And I also know that my sodium salt, NaA, will fully dissociate. That's a very clear assumption we will make in every buffer calculation. So my moles of A- are 0.0375. Now from there, I can also work out my moles of HA after dilution. I've got 0.15 moles. I know that because it's 1 decimeter cubed of 0.15 mole dm to the minus 3. Now that's been reduced by the 0.0375 moles of sodium hydroxide I've added, leaving me with 0.1125. I'm then going to rearrange my expression for Ka to make H plus the subject, as you can see here. And then I can start to put the figures in. Now the Ka is provided, the 1.79 by 10 to the minus 5, and you might have noticed that my HA and A minus, I've used molar quantities, but the expression calls for concentration. It actually works in this case, specifically because the volume is 1 decimeter cubed. Otherwise, we would have needed to divide by volume in each case. We go through there and we get an H plus concentration of 5.37 by 10 to the minus 5. I then substitute that into my expression for pH, giving me a pH of 4.27.